Hey everybody, Mr. Brown here. This presentation is about measurement and significant figures. So you may or may not have ever heard of significant figures, and on this slide I'm going to try to give you somewhat of a visual representation of what they mean and why we use them. Here in the picture we have a beaker filled with some substance. We're hoping it's apple juice, and we can see that the beaker is marked with cups down one scale and milliliters down the other scale. And we can see that the level of the liquid is sitting right at about the 1.5 cup mark. So we can pretty confidently say that we have 1.5 cups of liquid here in this container. But if I said to you that, or if I took this picture and showed it to you and I said that there was exactly this much, 1.5032, followed by some decimals, some more numbers behind the decimal there. If I told you that that level of liquid was equal to this exact number of cups, you probably wouldn't agree with me, or would probably think that that's not possible. And it's not, because our measuring system, or our measuring tool here, does not accommodate that much precision, and so we can't say that we have that much accuracy or that much confidence in the measuring of the liquid there. We can say with some confidence that we have about 1.50 cups of liquid there, but certainly not with the amount of decimal or numbers behind the decimal that we have at the bottom. Here on this slide, I am going to show you how we kind of determine how many digits we can use with our measurements. We generally say that our instruments are significant one digit past what they are marked for. Here in the picture we have what's called graduated cylinders, and these are commonly used to measure liquid volume in the chemistry lab. You guys will use these quite a few times throughout the lab portion of the course. And so I'm going to switch over to a drawn view of them so we can talk about how they were measured, but I wanted you to see what they look like in reality first. So when you measure with a graduated cylinder and you get down at eye level with the liquid in the cylinder, it will look somewhat like this. The first thing you may notice is that we have a dip in our liquid level, and that's from gravity pulling down on that liquid, and we call that a meniscus, and we always measure to the bottom of the meniscus. So this one right here, we see that that bottom of that meniscus falls directly on that line for our measuring scale, and we can deduce from this measuring scale that we have 10 marks between 20 and 30. So each of these is probably 1 milliliter. So this one would be 21, 22, 23. This is 24 milliliters. And because that falls directly on the 24 mark, we can pretty confidently say that this is 24.0 milliliters. For our next example here, we have this scale is marked with 5 lines in between every 10. So these seems to be marked in about 2 milliliter increments. And so if we're measuring to the bottom of our liquid level here, if this is 30, this would be 32, 34, 36, and that seems to be directly on the 38 mark. So this would be 38.0 milliliters. Again, in this measurement, we can pretty confidently say that it's 0.0 milliliters because it's right on that mark. Our measuring scale is not marked for that decimal place, but we can be pretty certain that it's there. In the final example here, this scale is again a little different. These are milliliters here with 10 markings in between. So these are, the little markings are 0.1 milliliter markings. So we'll notice that our liquid level here in this case seems to fall in between those two marks. And so that would be 2.1, 2.2, 2.3, 2.4, 2.5. It's a little more than 2.6, but not quite 2.7. So, and since it seems to be about halfway, what number would fall in between 2.6 and 2.7 about halfway? We can pretty confidently say that this measurement is 2.65 milliliters, because that is about halfway between 2.6 and 2.7. So this would be about 2.65 milliliters. We can, in each of these cases, we estimated 1 decimal place further than what our instrument was marked for, and all of these digits, all of these numbers would be considered significant, and we can be decently assured of their precision and accuracy. So as we're calculating things throughout chemistry, we have to make sure that we're not carrying through and making some measurements seem more precise or more confident than we think they are. And so we have to think about how significant figures are carried through when we do math on them and when we include them in calculations. And so the first thing we have to know to do is figure out which numbers in a measurement are actually significant. And these are your rules listed on this slide here that shows you how to figure out whether a number in a measurement is significant or not. And so the rules are: all non-zero digits are significant. Any zeros between non-zero numbers do count as significant. Zeros after the last non-zero count if there is a decimal. If there is not a decimal, they are not significant. And all zeros before the first non-zero number are not significant. And then finally, as a special aside, all numbers in scientific notation are significant. And so if you'll pay attention, what you're really doing when you're trying to figure out how many significant figures are in a measurement is you're really just trying to determine is the zero significant or is it not significant. Zeros can be just placeholders sometimes, and so they are not significant in those cases. And if you follow these rules, you'll be able to tell whether the zeros are significant or not.
Here on this slide, we're going to do some examples of counting significant figures in different presented measurements. And you can see on the first one, we learned on the previous slide that anything that is non-zero would be considered a significant digit. And so in this case, on the first one, there are 5 non-zero numbers, and I don't see any zeros in the measurement, so there are 5 significant figures, and you will also often see this abbreviated as sig figs. There are 5 sig figs in that first measurement. Our next measurement here shows 540.2 grams, and so we know that all of those non-zero numbers are significant. We have to determine if that zero is significant, and one of the rules on the previous slide was that any zeros between non-zero numbers are significant. This 4 is between a 0 and, the 0 is between the 4 and a 2, and so it is also considered significant, and so this number has 4 significant figures. This next number here, this next measurement here, 900,002.20 meters. Again, we're going to focus on the 0, and this time we have a lot more zeros to focus on. And we can see these zeros in here. We want to know if they are significant or not. one of the rules from the previous slide says that if they are between any non-zero numbers, then they are significant. And that goes for all of these zeros here. When we say, are they between, we mean anywhere to the left or the right of those zeros. If there are non-zero numbers, as there are in all these cases, all of these are between the 9 and the 2. So all of those zeros are significant. This zero has to look at another rule. It says that zeros to the right of all these non-zero numbers are significant when there's a decimal. And in this case, there is a decimal in this number. So all of these digits here in this number are significant. This was 1, 2, 3, 4, 5, 6, 7, 8 digits, and they're all significant, so 8 sig figs. In the next number, we have some more zeros that we need to look at. This shows 0.002827 grams. Now, we know that the non-zero digits here at the end are significant. And we also know that one of our rules from the previous slide says that all zeros, regardless of if there's a decimal or not, all zeros that come before the first non-zero digit are insignificant. They are not significant. So in this case, the first non-zero digit is 2. Any zeros that come before that would be insignificant. So those 3 zeros are not significant. There are only 4 sig figs in this measurement. On to the next one. The next one says 67 kilograms. We know that any non-zero digits are significant, so there are 2 significant figures here, no zeros to worry about. 67 kilograms has 2 sig figs. The next one, the next measurement, 50 pounds. Now we know that the 5 is significant since it's non-zero. This 0 is a question. So the rule says that any zeros to the right of the last non-zero digit. In this case, 5 is the last non-zero digit. Any zeros to the right of that are significant if there is a decimal. There's not a decimal here, so that 0 is not significant. There is only 1 sig fig in this number. This next one will test a couple of our rules that we've talked about so far. 0.0092280090. Ooh, there's a lot of zeros to worry about in this one. So we know that all of these non-zero guys here and here are significant, and we don't know about these zeros, we don't know about these zeros, we don't know about that 0 there at the end. We got a lot to consider, so let's take into consideration these zeros first. Let's mark our first non-zero digit, which would be the 9 here, and let's mark our last non-zero digit, which would be this 9 here. Alright, so we know that any zeros that come before the first non-zero digit are not significant. So these 3 zeros are out. We know that any zeros that land in between the first and the last non-zeros are significant. So these 2 are in. They're good. The only question that remains is the last guy here. He comes after the first one, or sorry, after the last non-zero digit. But there is a decimal in this number, so he is significant as well. Everything after the 9 there will be significant. So there is 1, 2, 3, 4, 5, 6, 7, 8 sig figs in that measurement. 56.70 grams. We only have one zero to consider here. It comes after the last non-zero digit, but there is a decimal in this case, so that zero is significant. There are 4 sig figs in that measurement. On to the next, 90.0 degrees Celsius. So we do have 2 zeros here. We have one non-zero digit, the 9, and so these two would come after the last non-zero digit. The 9 is both the first and the last non-zero digit. Both zeros come after the last non-zero digit, but we notice the decimal there, meaning that zeros coming after the last non-zero digit will be significant, meaning all 3 of these are significant for 3 sig figs in this measurement. In the next one we have 50 centimeters. So there's a decimal here. There's nothing after the decimal, but there is a decimal there. Notice that. We have one non-significant figure in the 5. It is both, again, the first and the last non-zero digit. So that 0 comes after the last non-zero digit. But there is a decimal, so that one would be significant. This is a 2 significant figure measurement. One of the exceptions that we had listed on the previous slide was that all numbers in a scientifically notated number are significant. So all 3 of these are significant, 3 sig figs here. And the next thing goes, the same goes for the next one as well. I know there's a bunch of zeros in here, but we don't even have to make the consideration. It's in scientific notation, so they are significant. There are 4 significant figures there. And then finally we have one with a bunch of ones and zeros here at the end. As you saw me do earlier on this slide, sometimes with these, the easiest thing to do is identify the first and last non-zero digit. The first and last non-zero digit, the first one is this 1 here.
Here on this slide, we have our first addition example. We'll notice the problem asks us to calculate 19.2 plus 42.81. We may remember from our significant figure rules that we're really paying attention to the number of decimal places when we are calculating additions and subtractions. And so we'll make note of the fact that this number, the 19.2, has one decimal place, and this number, 42.81, has two decimal places. When we punch it into our calculator, we see that the answer to this evaluation is 62.01. But we need to round our number to the lowest number of decimal places from our calculations, and that would be the one decimal place in 19.2. So we're going to round this number to one decimal place, remembering that 1 is not above 5, so the 0 will not change, and so the answer to that one in the correct amount of significant figures is 62.0. Here we have another addition problem, 81.417 plus 51.3254. Remembering back to our rules again, what we're really concerned with is the number of decimal places. In this figure we have 3 decimal places, and in this figure we have 4 decimal places. If we punch this in our calculator, it tells us that the result of this function is 132.7424. Remember, we want to round to the lowest number of decimal places in addition and subtraction problems, so we want to round this to 3 decimal places. We'll need to chop off behind the 4 to round to 3 decimal places, and so our answer becomes 132.74, and then the 2 is going to remain the same because the number being left off is lower than 5. So 132.742 is the answer here with the correct number of significant figures. We have another addition example here. We take note of how many decimal places are in our numbers being added, and we see that we have 3 decimal places in the 98.231. We have 3 decimal places in the 19.531. If we add those together in our calculator, it shows 117.762. Since we want to round to 3 decimal places, and we see that our answer already has 3 decimal places, that is already correct, and 117.762 is the answer to that problem in the correct number of sig figs. Here on this slide, we have the first multiplication problem that we're going to do with our significant figures. It shows 52.31 times 9.45. If we put that in our calculator, we see that the result is 494.3295. We may want to count how many significant figures were in the numbers that we multiplied, seeing as how we have to round down to that many numbers. So we have in the first one, all of these are non-zero, so that means we have 1, 2, 3, 4 significant figures in that number. This next one is also all non-zeros, so we have 1, 2, 3 significant figures in that number. And so we must round our answer to the lowest number of significant figures. In this case, we have 1, 2, 3, 4, 5, 6, 7 significant figures in the answer that the calculator gives us. And we have to round that off to only 3 significant figures because that's how many significant figures was in the 9.45. So if we're going to round to 1, 2, 3 significant figures, we have to round at this point right here, right behind the decimal. So we are going to round behind the decimal, and we'll notice the number here in this position, the 3, is lower than 5, so our 4 is not going to change. So that means the answer becomes 494. So to the correct number of sig figs, the answer to 52.31 times 9.45 is actually 494. Here we have a division problem, and we also remember that division, like multiplication, you round to the lowest number of significant figures from the numbers that you do the function on. In this case, we have 0.256 divided by 1.2634. The first number, that 0 is not significant because it comes before any other non-zero digits. So this number only has 1, 2, 3 significant figures. The next one has 1, 2, 3, 4, 5 significant digits because there are no zeros there. But that's a little inconsequential because we know we're going to be rounding down to 3 significant figures because of this number here. So when we punch this in our calculator, 0.256 divided by 1.2634, we arrive at the answer, pretty long one in this case, 0.20262782966, and who knows, it may keep on going from there. That's just where the calculator stops. So again, we know we're going to round this down to 3 significant figures. The first 0 in this number will not be significant because he comes before any significant or any non-zero digits. So our first significant figure starts here, 1. That 0 would be significant because it is in between non-zero digits, and the third one would be that 2 there. So we want to round off at this position. Now we have a case where the number we're rounding off is higher than 5, so we need to round this number up 1. Therefore, our answer should be 0.203 in the correct number of significant figures. We return to a subtraction here, and we notice that we have 1.52 divided by, or subtracts 3.98. And we notice that there are 2 decimal places in both figures. So we're going to punch these into our calculator. 1.52 minus 3.98. And the answer becomes negative 2.46. The answer has the same number of decimal places as both figures in the problem, so we can assume that that is the correct answer, negative 2.46. We have another division problem here with some really very small numbers, and we can see that we want to count how many significant figures are in each number because the division rules say we should round our answer to the same number as of significant figures as the number with the lowest that we performed the calculations on. And so this number has 2 significant figures. None of these zeros are significant because they come before the first non-zero digit. None of these zeros are significant because they come before the first non-zero digit. So therefore, this one has 1 significant figure. All right, so our answer will be rounded to 1 significant figure. So I'm going to punch 0.00026 divided by 0.0000005 into the calculator. And the answer I return is 5,200. But remember, we have to round this number to 1 significant figure. So therefore, we need to count how many significant figures we have. We have a non-zero, that would be 1. A non-zero, that would be 2. Now these zeros come after the last non-zero digit, so they would be significant if there was a decimal, but there is no decimal, so they are not significant. So they are not adding to the count. So there's only two significant numbers here in our number. We need to round at this position here to get to one significant digit. But we know in the past, because everything's been after that decimal, we've just been kind of cutting it off and throwing away. When you're on the other side of the decimal, you can't just throw all of that stuff away. You have to add zeros in. So 5,200, do we want to round it to 5,000 or do we want to round it to 6,000? That's decided. This is lower than 5, so it stays the same. So the answer there is actually 5,000. 5,000 only has one significant figure right here, and then these zeros are not significant because there's not a decimal in the number. So the answer is 5,000. We have another division problem here, 152 divided by 4, and we would count the significant figures in each number. We would see 3 significant figures in 152, and we only see 1 significant figure here in the 4. If we punch this into our calculator, it actually tells us the answer is 38, but we want to round that to 1 significant figure. So since the answer 38 has 2 significant figures in it, we are going to round it off at this position here. Again, we're on the side of the decimal where we can't just cut everything off and throw it away. We have to maintain that position. So this is going to round off into a 0. The 8 is going to round off into a 0. The only question is, do we change the number in front of it, yes or no? And so the 8 will change the number in front of it. So 38 becomes 40 rounded off to 1 significant digit. On this slide, we're back to multiplication. We have 0.002306 times 0.2541, and we will count the number of significant figures in our calculated numbers here. These 3 zeros would not be significant because they come before the first non-zero digit. So our significant figures start here. I see 1, 2. This 0 is in between non-zero figures, so he's significant. 3, 4 significant figures there. This 0 would not be significant because he comes before any non-zero digits. These are all non-zeros, so I see 1, 2, 3, 4 significant figures there. If we punch this into our calculator, the resulting answer is 0.00058595546. We're going to count the number of significant figures in that answer. These first zeros are not significant because they come before the first non-zero figure. So we have 1, 2, 3, 4, 5, 6, 7 significant figures in our answer. Because both of these had 4 significant figures, we want to round off to 4 significant figures. So we're going to round off at this position right here. We need to determine if the number before it is going to change our number, and it is 5 or higher, we'll change the number in front of it. But we see we already have a 9, so we actually need to change the 2 numbers in front of it because that 9 is going to jump up to a 10, but we won't write 10, we'll change the number in front of it to a 6. So that answer will actually end up rounding to 0.0005860 would be how you round that to the correct number of significant figures. Multiplication here, 6.5343 times 15.2232. I don't see any zeros in these numbers, so all digits can be assumed to be significant, meaning we have, looks like 5 significant figures in this number and 6 significant figures in this number, meaning our answer is going to end up with 5 significant figures. We'll punch in our calculator. And for me, that returns the answer 99.47295576. We'll count up all the significant figures in there. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 whole significant figures in that number because all are non-zeros. We're going to cut off at the 5th significant figure because our lowest number in our 2 calculations was 5. So we'll cut off at this position right here. Again, we see that this number in front is higher than 5 this time, so this is going to change the 2 here, and our answer will become 99.473. We have an addition with long decimals in this one, so we count and see that we have 1, 2, 3, 4, 5, 6, 7 decimal places in the first figure. We have 1, 2, 3, 4, 5, 6 decimal places in the second figure, so we'll round off our answer to 6 decimal places. If I type in 0, 0, 2, I return the answer 0.00034,016. And we want to round off at this position here because that would be 6 decimal places, and we're trying to round to the lowest number of decimal places. The 6 is greater than 5, so that's going to change our 1 to a 2. That means the answer to this one is 0.003402. Here we have an interesting one. 5 divided by 5. We know that for division problems, we always round to the lowest number of significant figures. You can probably easily see that both of these have only one significant figure. We know that 5 divided by 5 is 1. We know that 1 has one significant figure, so everything checks out there. What about when we multiply 5 times 5? We again remember that we want to round our answer to the lowest number of significant figures, and that 5 and 5 each only have one significant figure. So when we write out the answer to this, 5 and 5 equals 25, we may notice that our answer has 2 significant figures. We want to round that to one significant figure. So if we're going to round 25, which has 2 significant figures, to just one significant figure, we need to decide whether to change our 2 to a 3 or not. The 5 is 5 or higher. That's going to change our 2 to a 3 and cause our answer to become 30. So the answer to 5 times 5 with the correct number of significant figures is actually 30. Back to some more reasonable measurements. 15.24 times 6.0 is a multiplication problem, so we round to the lowest number of significant digits. In this case, 15.24 has 4 significant digits, and 6.0 would have 2 significant figures. The 0 is significant because it comes after the last non-zero digit, but there is a decimal in the number, so it is significant. There is 2 significant figures in the 6.0. When you multiply those numbers out, 15.24 times 6.0, the calculator returns 91.44. Now again, we want to round this to two significant figures since that's the lowest number in our operators. And so this number has 1, 2, 3, 4 significant figures since they're all non-zero. And we'll want to round at this place right here. The 4 will not cause the 1 to change, and so the answer to that operation in the correct number of significant figures is 91. We have another division problem here, so we'll be rounding to the lowest number of significant figures in our operators. We see that we have all non-zeros in these, so that means these are 3 significant figures here in this number. These are 6 significant figures here in this number. And when we calculate it out, we receive the answer 0.00759 749992. So for this number, we want to know how many significant figures there are. Those zeros in the front are not significant because they come before any non-zero digit. So we'll start our significant figures here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. In this number, we want to cut it off at the third because our lowest number is 3 in our two calculating numbers, and so we'll cut it off here. We're going to look at the number before it. Our 7 here is higher than 5, so it's going to change our number here. Again, we have a 9, so that's going to become 10, which we show with a 0 and changing the next number in the line. So that rounds to 0.00760. We have a multiplication design trips up a little bit here. We see the operation 20 times 220. We remember that multiplications rely on counting the number of sig figs and rounding down to the lowest number of sig figs from our problem. 20 times 220 returns the number 4,400. We know that this one only has one significant figure here. That 0 is not significant because he comes after the last non-zero digit and there is no decimal. The same thing goes for this 0. He comes after the last non-zero digit and there is no decimal, so there's only 2 here. But regardless, we still have to round down to just one significant digit. 4,400 has 2 significant digits, 1, 2. Those zeros are not significant because they come after the last non-zero number. And so we are going to round this number at this position here. The 4 will not change the 4 in front of it, but we need to keep our places, so we'll just change that 4 to a 0, and 4,400 rounds to 4,000 if you only want one significant figure. In this case, we have mixed operations to determine how many numbers of significant figures we're going to use. And so if we remember our order of operations rules, things in parentheses are done first. So we're going to do the addition first. 1.243 plus 4.2 equals 5.443. So I'm going to rewrite this 5.443 times 20.3. But we need to round this off to one decimal place. So these decimal places here, 1, 2, and 3, need to be rounded to one decimal place. This 4 will not cause the 4 in front of it to change, so what we really should write is 5.4 times 20.3. This number, 5.4, has two significant figures. This number, 20.3, has three significant figures. When we multiply them together, we should round our answer to two significant figures. 5.4 times 20.3 becomes 109.62. But remember, we want to round our numbers to two significant figures. So we're going to count the number of significant figures in our answer here. I see 1. This 0 is significant because it's between non-zero digits. 2, 3, 4, 5 significant digits in that number. We want to round off at this position here to go down to two significant digits. And so we look at the 9. The 9 will change that 0 to a 1. And we want to keep at least the 0 for the 9 so that we know that where our decimal lies. So 109.62 rounds up to 110 with the correct number of significant digits.